Remember I was talking about the cumulative mass number? So for example, H2O, there's a cumulative mass number. So H2O, let's say H1, O16, H1 had a H2O mass number of 18. 18 means what? 18 total. You guys have a chance to review mass number, atomic number, all that stuff? This stuff is easy to forget, like I said before, and so really I think the trick to remembering is just to have it in your notes and just read it every day. And then if you see the mass number is the number of protons plus the number of electrons, and it should hopefully be automatic, so it's quick. So if you saw it on the test, you'd know, oh yeah, number of protons and number of neutrons. But does the mass number tell you how many protons and neutrons there are? So if you had a mass number of 16, there's a certain number of protons, a certain number of neutrons we don't know, because there are two unknowns, one equation, so we need another equation to figure it out. And so what people have done is to say, okay, I know that there are, let's say, 16 protons and neutrons. I'll just call those nucleons. And so a nucleon is either a proton or a neutron. So, mass number of 16 has 16 nucleons. Now you got to figure out how many of those nucleons are protons and how many of those nucleons are neutrons. And so that's a word. I'd never mentioned nucleons, but if it's in the homework, then usually the homework is fair game for tests, is what they say. But some of the homework I don't. I mean, some of the homework is just getting too much into physics or this. So you get a sense of that from going to class and seeing what's
when it comes to
more
like
important.
the mass of an electron or mass of proton, neutron, or electron, would those be given to us?
No. The thing is, okay, for the mass of a proton and neutron, you should know approximately what is the approximate mass of a proton and neutron. And the reason you should know that is because the mass number is close to the actual mass. Why is the mass number close to the actual mass of the atom? Not exactly, but close. So, for example, oxygen 16 has a mass number of 16, and the actual mass is very close to 16. Why is that?
Because protons and neutrons are
About 1 U. Do you know that? If you know that, then that's enough. That's all you need to know. They have a mass of about 1 U. Now, if you looked at the table, this is what you do. When you want to really study, do you memorize the table? No, I don't memorize the table. And so if I go back to the nucleons, or the protons and neutrons, here, this is what I do.
Bless you. Thank you.
I don't remember what page that was on here. Or the next page. I wrote the book so I could just quickly see what page that was on. Page 44. Oh, just one more page. Something's wrong with this. Sometimes it does this, where it jumps from page to page. Am I going to memorize these numbers? No, not at all. In physics, I actually did. I memorized some of these numbers in physics. Will I memorize these? Probably not to 5 sig figs. I'd probably memorize these two, 1 or 2 sig figs. If you go 2 sig figs, what is this? And 2 sig figs here? That's pretty easy to memorize, isn't that? So the mass of a proton is 1.0, the mass of a neutron is 1.0. Are they the same mass? No. Which one's heavier?
Neutron.
Neutron's just slightly heavier. Not that you really need to know that, but just slightly heavier. An electron is about 2,000 times lighter. So I would memorize it 1.0, 1.0.0005, 2,000 times lighter. Not exactly, but close enough. So that's what I do. I wouldn't memorize any of the other numbers. So do you have to know the mass? Yeah, you have to know the mass of protons about 1 and the mass of neutrons about 1. That's why the mass number and the actual mass are so often confused. They aren't the same thing, though. All right, so going back to 22, what was the question for 22? Determine, oh, okay. There was an error in this one. Did somebody see the error? M over E. M, do you know what M stands for? Mass, and E is
Electron.
Speed of light.
the charge. The charge. And so, do you know the charge of an electron? Well, then, the charge of an electron is -1, but -1 is like the quantized unit. The actual charge is -1.6 times 10 to the minus 19 coulombs. Right? And so, well, all we do is we take the mass. Now, the mass number is going to be close. So if I want to guesstimate it, we could guesstimate it. 127 would be the approximate mass of this. Or what I do is I just look up what is the actual mass of iodine 127. And so I could look that up. Where would I find that? You know where I'd find that, most likely? This is, this is something that surprisingly people don't do. Actually, I don't know. I have to do this. Where have you seen the masses of isotopes? Yeah, a table and this is so slow. Show it faster. A table and appendix D, data tables. Appendix G, answers. You didn't get the solutions guide, you get this. However, there's so many different tables here that I don't want to go through them one by one, so take a look at which Appendix D table that was. See, what are we looking at? Iodine? Iodine's element number 53. E33. So I'm going to go to A33 here. How many different naturally occurring isotopes are there of iodine?
One.
Only one. Only one. It's iodine 127. But you know the nuclear meltdown, Fukushima. There's a whole bunch of radioactive iodine that was released. Radioactive iodine is not 127. I think it was 128, maybe. What was it? the radioactive iodine. And so after the meltdown, in which a lot of radioactive iodine was dispersed into the air and the land and the water, people consume it. And iodine, you know where iodine accumulates in your body? Like, if you don't have enough iodine, you can suffer from this disease.
Thyroid?
Yeah, thyroid. Your thyroid. And so if you don't have enough iodine, if you have iodine deficiency, all that radioactive iodine concentrates in your thyroid, and you end up with thyroid cancer. The treatment for thyroid cancer is they just remove your thyroid, but then you have to go on some kind of hormone therapy afterwards. And so after Fukushima, a lot of people lost their thyroid, had it removed. You know Chernobyl? Chernobyl also released a lot of iodine, and some countries in Europe gave their citizens, especially their kids, iodine supplements. They took the iodine supplements to saturate the thyroid with non-radioactive iodine to prevent radioactive iodine from concentrating in the thyroid. Those countries that did that saw a much, much lower thyroid cancer rate than the countries that didn't do that. A lot of people recommended that to the Japanese government, but the Japanese government said, oh, our population eats lots of seafood, and seafood apparently has a lot of iodine. But still, there are people who actually, the incidence of thyroid cancer is much higher than what normally would be expected. But, that's what happens when these accidents happen. Accidents happen, and oftentimes the government or the authorities try to downplay the severity of it. Like Palestine, Ohio. In fact, there's talk about you guys heard about the Palestine thing in Ohio, all the chemicals, vinyl chloride and all that? Well, they're going around. There are different ways we can test what the chemicals are. They have these handheld testers. These handheld testers aren't very specific. They just generally tell, okay, there's this much kind of organic matter in the air, but they don't tell you what that is. Or they test the water. Instead of that, what do you want? You want to know everything in the water, and you want to know how much, right? That's called quantitative analysis. When you're breathing the air, you want to know how much of everything is in there, And so typically what we want to do is we want to analyze it. And so they're talking about there's not enough analysis. Normally, you know how samples like that are typically analyzed. Did I talk about this? No. You collect an air sample or water sample in a container. And then how do you figure out what's in it? Because this is a complicated mixture. And so the first thing you do is you introduce it into... Well, anyway, let me finish off with this. So here's the mass, and the charge is negative 1.6. So you take the mass, U, divided by the charge. Do they want the mass in U, or do they want the mass in grams?
Grams.
Okay, so do you know the conversion between U and gram? Did I talk about that?
Yeah.
It's really easy. The conversion between U and gram is what?
The mole. What's the number?
Yeah, it's the Avogadro's number, right? When I memorized it in physics, I had to memorize it in physics. It was like 1.67 times 10 minus whatever, 19 or 21, I forgot. Actually, I don't use it very much. That number. And that's the number I had to memorize. It had no connection. All this time I had to work at memorizing it. And memorizing things isn't easy. It takes a lot of time to memorize it. And so I memorized it. I'll tell you what the number is. Because, well, I don't have to have it memorized. I could easily derive it if I have a calculator. Number was 1.6606 times 10 to the minus 24 grams per U. Hard number to memorize. I don't know why they didn't do this. They didn't do this because physicists don't have to memorize Avogadro's number. The chemists have to memorize Avogadro's number. And this is so much easier to memorize. I wish I had known this when I was taking physics. Because then I would have never forgotten it. This one I've forgotten numerous times and had to look it up in a book. I didn't know how to calculate it at the time. It was so easy to calculate. You know where I got this number from? I just inverted this in my calculator. I took Avogadro's number, 1 over that, and that's what the number you get, right? Does that answer the question, Gabe, about the number 22?
Yeah.
Yeah. All right. So getting back to the story, if you really want to know what's in the air you're breathing, what is it? Then you want to know all the substances in there. And how do we identify the substances? We identify the substances by their composition. And it's not usually percent by mass composition. If somebody told you, okay, there's a substance in the water that you just consume containing 11% hydrogen, 89% oxygen, are you going to worry? 11% hydrogen, 89% oxygen, and it turns out that this substance is in water in very high concentration. Are you going to start to worry? I wouldn't either. I would be happy if my water contained lots of that, because do you know what that is? A substance that contains 89% hydrogen by mass and 89% oxygen by mass and 11% hydrogen. Do you know what that is?
Is that just H2O?
It's known as H2O. H2O is known as, because hydrogen is very light, and so it's only 11% hydrogen by mass. Or somebody told you that there's a substance in the water and it contains 67% hydrogen, 33% oxygen. Are you going to worry? No, I wouldn't worry about that either, because that's by atom or by mole. But that's not normally the way we think of substances. The way we think of substances is by the formula. The formula tells us the mole ratio. 2 atoms of hydrogen, or 2 moles of hydrogen atoms, and 1 atom of oxygen, or 1 mole of oxygen atoms. This is the mole ratio. So if we want to know what's in the water or in the air that you're consuming, then you want to know all the substances. What are the formulas for everything in there and how much? If this was 100% H2O, then don't worry about it, right? That's pure water. And so what they do is, and this is what they want to do, but it's not easy to do, because what you do is you collect a sample, and then do you know what you introduce it into? You introduce it into a machine called a GCMS. GCMS. GCMS stands for gas chromatography mass spectrometry. And so when you introduce the mixture in there, let's see if they show a schematic of this. You introduce the sample in here, and it gets picked up by a stream of gas, like helium gas. And it travels through what's called a column. And in this column, there's a resin or a stationary phase. And what happens is some molecules are more sticky, some are less sticky. So depending on how the molecules interact with the stationary phase, it will impact how fast it goes through the column. So the less sticky ones go through here fast. The more sticky ones go through here slow, and the stickiness is dictated by the intermolecular forces of attraction between the molecule and the stationary phase. And in this way, if the column is long enough, it can separate out all the different substances in the water or in the air sample. It's like if you're at the start of a marathon, everybody's bunched up together, so you can't tell the difference. Everybody's kind of running at the same speed at the start, right? But by the end of the marathon, is everybody bunched up together? No, everybody's going to be separate, so it's easy to tell the difference between, the faster ones and the slower ones. And the same thing here. It's easy to tell as long as this column is very, very long, which it is. It's very, very long. So it can separate things. And then you know what you feed it into? A mass spectrometer. But a mass spectrometer gives us more information. So far, what information does a mass spectrometer give you? It tells you 3 things. What are the 3 things a mass spectrometer tells you?
How many isotopes?
How many isotopes? Good.
Like percent abundance of
The
those.
percent abundance of each of the isotopes. And the mass of each isotope. And so iodine-127, we can weigh it. But do you know it can give you more information? If you feed molecules in here, it can give you the mass of the molecule. But if it gives you the mass of the molecule, then we can't tell the difference between certain, what we call isomers. So it's important how you write a formula. So if I wrote a formula C2H6O, you know, it's going to weigh a certain amount. And the problem is, with this formula, I can't tell what it is. You know, I can't tell what it is because of something called isomers. Isomers are same formula but different structures. So this could be ethanol, CH3, CH2OH. Could be ethanol, you know, or C2H5OH. But ethanol weighs exactly the same as something else called diethyl ether, or not diethyl, dimethyl ether. Dimethyl ether and ethanol have the same formula, different structures. You could drink ethanol, but you wouldn't want to drink dimethyl ether. This would be much more poisonous than ethanol. But they weigh the same amount. So if you fit this into this mass spectrometer, it's going to hit at the same place because they weigh the same amount, correct? But if you change the gun, you know, there's like an electron beam here, electron gun. Rather than shooting electrons at these, if you shoot small molecules at these, or charge, yeah, if you shoot small molecules at these, do you know what happens? It breaks it up and fragments. Ethanol, if you break it up by shooting small molecules at it, it's going to break up differently or fragment differently than dimethyl ether. And so based on how these molecules fragment, and detecting the fragments here, you can just use a computer and identify everything. And so it's easy to tell the difference between, let's say, ethanol and dimethyl ether in a mass spectrometer too. So there's more information that you can get from a mass spectrometer, not only the three that I'd mentioned. And so this is what they want to do. In Palestine, they want to analyze all the soil samples, the water samples, and everything else using a technique that can identify all the compounds present and how much. You know, so if you're worried about vinyl chloride, you know, the OSHA limit for vinyl chloride is 1 part per million. Are you over 1 part per million or under? You know, the water that the mayor or whoever, or the EPA was drinking, did that have more than 1 ppm? It could have more than 1 ppm as long as you don't drink it over the entire year. You know, if you just drank it once and that was it, then that was purely for show. But if you had to drink it day in and day out, every day, you know, then your tolerance is going to decrease. Your tolerance will be much higher if it's just one exposure. And so they have different tolerance limits depending on how much you're exposed. When I was working with x-rays, they had a certain tolerance limit set. So I could be exposed to a blast of x-rays, but if my badge says, okay, you've had your dosage for the entire year, I couldn't work anymore with x-rays. And so I had to wear a badge, and then the badge is kind of ridiculous because the badge you turn in every month, and then they tell you, oh, you've exceeded your dose of x-rays, and therefore don't work anymore, you know, for this amount of time. Or maybe you're still under. And so it's like, okay, if you're working there and living there, it's a different story. So but anyway, getting back to this, what we want to know is we want to know all the compounds or substances, I mean, it could be elements there too, compounds and elements present in the water and air samples. We could do that using GCMS and some other techniques too, but this is the main one. They have portable units for these, but these aren't handheld. You see people analyzing, you know, the air and the water samples with these handheld ones. Those aren't GCMS specs, you know. If they pull up in the truck and this thing's mounted inside the truck, then yeah. If they're using these little handheld units, we don't know what it is. Is it this? which you can drink, or this, which you can't drink. Can you tell the difference? Not with those handhelds, you can't tell the difference. And the handhelds don't weigh it anyway. Were there any other questions before I get in? I'm starting chapter 3 again.
Yeah, for 25, why do they, on the book, on the answers, why do they have a superscript of A? So for instance, they have it labeled for the name of the, like for instance, they have, yeah, like arsenic.
Well, A is just the symbol that we give to what? A is called the. I didn't review this.
No, not that.
Not that
For
A?
instance, protons, it has 33 to the power of A. What does that mean?
Where do you see that? Number 25?
25 for the answer key.
For which element?
Arsenic.
Arsenic, okay. Arsenic is element number 33. So that must be this one here.
Yeah,
It's
it's the
neutral.
number of protons, it has 33 to the power of A, and I didn't understand.
No, that is a typo. Arsenic is Z. Z is equal to 33, which is equal to the number of protons. A is usually refers to a footnote. So otherwise, it's just a number.
So what would the footnote be?
The footnote, is it in the solutions guide? I didn't bring the solutions guide.
Yeah, you're right. It says this result assumes that a neutral atom is involved.
Okay, yeah. Yeah, that would be for the number of electrons. You know, if it's a neutral, then the number of protons would be the same. If it's not neutral, then the number of protons, who knows what it is, you know? And so this has got to be the footnote. Yeah.
Okay.
Okay, other questions?
So I guess going back to the proton and neutrons.
Mm-hmm.
So like let's say you have something that has like 7 AMU, but it's really approximately 6.8 AMU.
Uh-huh.
Is that because some of its mass is going to be gone? Going back to like energy equals to mass times c squared?
Yeah.
Okay.
Yeah.
Can you explain more about that if it's relevant?
There's was there helium in this chapter? They did for the mass defect. Did they do helium? Do you recall reading about helium? No? Okay, mass defect involves what? Mass defect involves chemistry or nuclear chemistry?
Nuclear.
Nuclear, but it has an impact because it means that we have to weigh things and not sum up the masses. Do you know? I don't know if your book should have chapter 25 or chapter. I don't know if they changed the chapter. I talked about some of the mass being converted into something called the nuclear binding energy. Some nuclei are very strong and because they have very high binding energies. And this is the nuclear binding energy per nucleon here. And so the strongest nucleus is going to be here, because it has the highest. And so this nucleus has the most mass that's been converted into energy. Some of these weaker ones here and here, like the light ones aren't as stable and the heavy ones aren't as stable. Here. These are some rules that they observe. We have something called magic numbers for nuclear stability. These are just observations. I talked about even-odd rule. Even-odd rule. I didn't talk about this, the proton to neutron ratio. I don't know, I can't remember what chapter helium was in. But there's a homework problem. Did I sign the one with fluorine in the homework? I'm pretty sure I did. Yeah. Number 69. Has anybody done that? Number 69? Maybe should maybe I should talk about it after you guys have had a chance to look at this, or right now? You want me to do it right now?
After.
After?
We have some, like
Yeah.
maybe after the next lab.
Well,
Or sorry, like the next day. Like
yeah. Actually, this is week 3. So week 4 we have our first test next week. Well, yeah. Number 69. I'll just show you the problem here. Let's see it. This is a mass defect problem. Number 69 says fluorine has a single atomic species, fluorine 19. Determine the atomic mass of fluorine 19 by summing the masses of the protons, neutrons, and electrons. And compare your results with the value listed on the inside front cover. Since fluorine only has one isotope, all fluorine atoms weigh this amount, the amount in the periodic table. This is not an average. Each fluorine atom weighs 18.998403 U. So we know how much a fluorine atom weighs. And so what we're going to do is we're going to compare the sum of the masses of the protons, neutrons, electrons with the actual weight. Which one is going to be heavier? The sum is going to be heavier because some of the mass of the nucleus is converted into the nuclear binding energy to hold all the protons together. Fluorine has 9 protons in the nucleus, and so you need a lot of energy to hold those together. Otherwise, electrical repulsions will break it apart. And so this is an example of explain why the agreement is poor. The agreement is poor because of the mass defect. The actual mass is less than the sum of the cumulative masses. That's as much as you need to know. Actually, calculating the mass defect is, you could do that in chapter 25, nuclear chem. You do calculations, how much energy is converted, and you use this equation. And so in chapter 25, we actually do calculations, but these calculations are really easy. Delta E is equal to delta MC squared. All you have to do is you have to convert U into kilograms, and then you get it. C is the speed of light in meters per second. And so it's meters squared per second squared, kilograms. You know what a kilogram meter squared per second squared is? A joule. That's the definition, the physics definition of a joule. Kilogram meter squared per second squared. And so you can calculate delta E in joules pretty easily. And this is chapter 25. Chapter 25 energy calculations are pretty straightforward. The mass defect not only happens for the nucleus, the mass defect happens for chemical reactions. In chemical reactions, Lavoisier back in the old days said mass is conserved. So if you have the reactants and you weigh those, and you have the products after reactions occurred and you weigh those, the mass is the same, right? In nuclear reactions, the mass isn't the same. And so in nuclear reactions, the reactant mass does not equal the product mass. There's a mass defect there too. Mass is not conserved. It turns out when people dug deeper, it's both in chemical reactions and nuclear reactions, mass is not conserved. It's just in chemistry, the energies, which are bonds, are so small, so minuscule you can't measure the mass difference using balances.
So, you know how when you think of something being conserved where, let's say matter can't be destroyed or created, you know you have a chemical reaction, for instance, and it does like the exchange of ions. But when it comes to this nuclear chemistry, what exactly happens to the mass? It just like disappears? Is that basically what happens?
Things don't weigh. You still have all the pieces. Well, essentially all the pieces there. Nuclear reactions are pretty simple. All the pieces are still there. You know, so for example, there are different types of nuclear processes, like that emit radiation. Like, for example, a neutron. You know, have you heard of beta radiation? Beta radiation is, let's say you have too many neutrons. One way to get rid of a neutron is to convert it into a proton. So you can take a neutron, convert it into a proton. A neutron has a Z of 0 and a mass number of 1. And so this is Z and A, this is Z and A. But all the pieces are still there, and so what you need is this, a beta to be emitted. A beta is a 0, -1. That is that right?
Should the negative number in the bottom?
On the bottom, yeah, 0 and -1. And the beta particle is an electron, essentially, that originates from the nucleus. There are no electrons there, it's just a product of a neutron being converted into a proton. And so, you know, everything's still there. It's not like things disappear and appear. You know, it's kind of balanced, but in the nuclear sense of the word. And the masses don't quite equal out. That's the only other thing. But nuclear reactions are not too difficult to deal with. There aren't that many, and they're pretty straightforward. Okay. Any other questions? We move. So anyway, we want to know the composition, you know. So if you're in Palestine, you want to know what the composition of the water is, and you want to know what the composition of the air is. Now both of those are mixtures, so we want to know all the components of the mixture and how much. And so typically when we have some unknown, let's say some unknown contaminant in there, how do we determine it? Well, we send it out for chemical analysis. Not everybody has a mass spectrometer, GC mass spectrometer. Actually, we do. We have it, but it's sitting, kind of defunct, hasn't been maintained or used. Like, and most schools have it. Like at UCLA, we had a GC mass spectrometer. So one of the experiments that I did was I got gasoline samples. So I went to I think there's Shell and Chevron. So I got some Chevron premium gasoline and some Shell premium, and then also the regular gasolines. And then all I did was I fed the gasoline samples into the mass spectrometer, and then I got the breakdown. What's in that gasoline and how much of each compound there is. It's really Easy to do, and you can figure out what the composition of that mixture is quite quickly. But there are other techniques as well. So, like say GCMS. GCMS is easy, but you can't analyze everything using GCMS. So, for example, if they send something out to the moon and they want to analyze, the composition of some lunar rock, are they going to bring a GC mass spec out there? No. They have other tools. Another tool that they could use is something like XPS. In fact, I think that's what they brought to the moon. XPS. XPS stands for X-ray photoelectron spectroscopy. And what they do is they bombard the sample with X-rays. And what happens is it knocks out electrons off atoms. And what then happens is if you knock out electrons, it's unstable, so then the electrons reshuffle. So let's say you knock a core electron off, then the electrons reshuffle, that is, an electron drops in energy. When an electron drops in energy, it emits light. And so X-rays to bombard the sample, and photo, because it's emitting light, and you measure it, and spectroscopy is you measure the spectrum of this emitted. And you get a fingerprint, kind of a fingerprint of the atoms. Not only that, you could tell more information. You know, you can see valence electrons, how many core electrons, etc., depending on the electrons you knock out. And so this is another technique that's used, XPS. Then there's atomic absorption spectroscopy. Atomic absorption spectroscopy is, certain elements give color to flames. And some of these are not visible. Some are infrared, some are UV. Did I tell you I was watching TV one day and I was channel surfing? And then I saw this guy doing flame tests. And what a flame test is, he dips a platinum wire in a solution and then introduces it into the flame. And so if you put sodium in the flame, you get a bright yellow-orange flame. If you put lithium in the flame, you get kind of a red, purple, lavender color. And so
barium like red or something?
Barium, I think, is green.
Green.
Yeah, and then there are a bunch of others. And so, actually, and then I thought, wow, there's chemistry on this TV show. And then I started watching it from then. I had no idea what the show was, but you know what this show turned out to be? Does anybody remember? Somebody doing flame tests, some chemistry teacher doing a flame test?
Was it Bill Nye or something?
No. It turned out to be Breaking Bad, yeah. That was, anyway, that was when he was teaching in the high school. So, this is a quantitative version of that. The quantitative version is you measure how much light is given off. And then, depending on how much light is given off, you can tell how much of that element is present. And so these are quantitative techniques, AAS, etc. Okay, from this kind of analysis, we don't get a breakdown. Like GCMS will get a breakdown. What compound is it and how much there is. In this type of analysis, we typically get these kind of results. The results we get are either going to be in one of two forms. One, we'll get the sample mass and then the mass of each element. Present that they analyzed for. Or two, if we have the sample, the total mass and the mass of each element, then we can get the percent composition by mass. So if I weigh, let's say, 18 grams of water, which is a mole, I'd have 2 moles of hydrogen, which would be 2.016 grams, and 1 mole of oxygen, which would be 16.00 grams, and then I can figure out the percent composition. And so water is about 11% hydrogen, 89% oxygen, something like that. You could be more precise, more digits for this. Okay, if I have these, then what I do is, if I have number 1, I'll convert it to number 2, just by doing calculations. And so an example is the percent hydrogen in H2O is equal to 2 times the mass of hydrogen. I'm going to use 1.008 for the mass of hydrogen because I want 4 sig figs. Divided by the total mass. The total mass of an average water molecule is 18.02 times 100%. So I said 11%. Was I right? Was my memory right? I haven't done this calculation in a long time. So that's going to be 2.016 divided by 18.02 times 100, which gives me 11.188% hydrogen. So water has 11.188% hydrogen, and the rest is oxygen. So it has to add up to 100%. Therefore, it's got to be 99.888% oxygen, right? Because there's nothing else in there, just hydrogen and oxygen. Oh, not 99, 89. or 88. Did I get that wrong? It can't be 99. It's going to be 100 minus 11.18. 11.188 equals, sorry, I got it wrong. It's 88.812% oxygen. They have to add up to 100%. All right, once I get the percent by mass composition, then I assume 100 grams sample and I convert it to grams. Then I go from grams to moles, and then I go from moles to the simplest mole ratio. You know what we call the simplest mole ratio? Yeah, the empirical formula. So simplest mole ratio, which is the empirical formula. And then either I stop here or I continue to the, not the empirical formula, but I continue to the no, the molecular formula. If it forms molecules, then I want to know the molecular formula. But in order to get the molecular formula, I need additional information. The additional information I would need to know would be the molecular mass or molar mass or formula mass. Formula mass, yeah, work too. It has to form molecules. Does everything form molecules? For example, does helium form molecules? No. And so for helium, what we'd say is this is the atomic mass or the molar mass or the formula mass. Sodium chloride. Does sodium chloride form molecules? Sodium chloride form molecules? Well, if it doesn't form molecules, what else could it form? Ionic lattice, covalent lattice, metallic lattice, gaseous atoms and molecules. Well, it would do. No. And so in this case, we don't call it molecular. We would just call it formula. What am I saying? Mass. Formula. Unit. You guys heard formula units? Here we would be talking about formula mass if we're dealing with mass. And in this case, we talk about formula units here because it doesn't form molecules. Whereas H2O, we could have this. We could have molecular mass or molar mass. I forgot molar mass here. At H2O, we could have molecular mass, formula mass, we'd have molecules, or we'd have formula units. All these would be empirical formulas. Empirical formulas are just the simplest. In the case of water, the empirical formula is the same as the molecular formula. So the way we figure it out is we weigh the molecule. So if I had hydrogen peroxide, H2O2, that's not the empirical formula. What is the empirical formula of H2O2? Yeah. And so the empirical formula, EF, is HO. how much does an HO weigh? HO weighs about 17. Right? Oxygen 16, hydrogen 1, so it weighs about 17. Now, if you weigh the molecule is not going to weigh 17. The molecule is going to weigh 34. And so if the actual molecule weighs twice the empirical mass, then we know that the actual molecule is twice as big as the empirical unit. And so we'll need that one additional piece of information here. All right, so here we're going to just assume 100 gram sample. Okay, we really aren't going to talk about XPS. You don't need to know what XPS means or how it works. You don't need to know AAS. All you know is this is chemical analysis. And in this particular chemical analysis, this is what we call elemental analysis. Elemental analysis just looks at the elemental composition of the substance. And so for water, it's 11% hydrogen and 89% oxygen. Whereas in GCMS would actually determine it is water that's striking the detector there. There's another technique for elemental analysis, and it's called combustion analysis. Which I'll talk about as well. Combustion analysis only works for things that burn, that you can combust. And so let's do an example of this chemical analysis first, and then we'll do an example of combustion analysis, or maybe two examples of combustion analysis after that. Okay. Fortunately, my combustion analysis problem closed. I'll have to go back to it here. Not combustion, sorry, just elemental analysis problem. So number 88, by analysis, a compound was found to contain 26.58% potassium. So we send it out for elemental analysis, and then we get a breakdown of what elements are present and how much. So this compound has 26.58% potassium, 35.45% chromium by mass. The remainder was oxygen. And so how much oxygen did it contain? Well, if there are only three elements, those three elements must add up to 100%. And so the percent oxygen is just going to be 100% minus how much potassium we had, 26.58% potassium, minus how much chromium we have, which is 35.45% chromium. And this is going to give us the percent oxygen. So let's calculate how much oxygen there was. 100% minus 26.58 minus 35.45. And I calculate 37.97% oxygen. Okay, so once we have everything in percentages, then if they weren't, we convert it into percentages. Then we figure out how many moles, because, well actually, no, we figure out how many grams by assuming a 100 gram sample. So if I had a 100 gram sample, then it's going to be 26.58 grams of potassium and 35.45 grams of chromium and 37.97 grams of oxygen. Hey, can you name this compound for me? What is this compound? Do you even recognize this compound? You probably don't recognize this compound because nobody ever lists compounds based on their percent composition by mass. Everybody lists compounds by either their empirical formula, but even the empirical formula is tricky. They'd rather use just the molecular formula or just the formula. And so the next step is, a formula is a mole ratio. And so mass ratio is not going to do it for us. We can't recognize this, and I can't write down what it is. And so what I'm going to do is I'm going to convert grams to moles. So I need the molar mass. I'll just get the molar mass off the periodic table. So potassium, I round to 2 decimal places. Potassium is 39.0983. 39.0983. 39.0983, I'm just going to round to 39.10 to 2 decimal places. And so 1 mole of potassium weighs 39.10 grams. And so that's going to give us how many moles? And so I'll just do 26.58 divided by 39.1. 0.6798. And the next digit's 0. I'm allowed 4 sig figs. I'm going to use all of them. And so this will be moles of potassium and then some. I'll carry 1 extra digit. The reason I carry 1 extra digit is because when we figure out the formulas, you know, if I start rounding, it screws up the ratios oftentimes. We want simple whole number ratios for formulas. Okay, chromium. The molar mass for chromium off the periodic table is 51.9961. 59.9961. So what I'm going to do is I'm going to 51. I'm going to round it to 2 decimal places. So I'm just going to round this to 52.00. And so 35.45 divided by 52 is going to give me 0.68173 moles of chromium. And then oxygen I don't have to look up because I have it memorized. Do you have it memorized at 2 decimal places?
Yeah.
What's oxygen?
16.00.
Yeah, 16.00. So 1 mole of O weighs 16.00 grams. And what's that going to give me? 37.97 divided by 16. 2.373. 2.373 sub 1 moles of oxygen. So a chemical formula is the mole ratio. And so what I'm going to do is I'm going to get the formula for this. The formula is going to be K 0.67980, CR 0.68173, O 2.3731. Now can you name this for me? No. In fact, this would be a violation of what law? Is one of the successes of Dalton's atomic theory. Dalton's atomic theory predicted this law. What is that law? So again, this is just another case. You might think, this is a bit of memorization, but the memorization is made easy if you read it every day. So if you have it in your notes and you looked at it every day since then, it's a lot easier to recall information. A lot of tests are just recall of information. Do you remember it or you don't remember it? If you've never seen it, Versus if you see it every day you see that. And there's a big difference.
The ratio.
Law of multiple proportions. Law of multiple proportions just says that the atoms should be in simple whole number ratios. Are these numbers in simple whole number ratios? Not even close. Not even close. So what do we do?
We divide by the smallest number.
Yeah, we divide by the smallest. The smallest is going to be 0.6798. 0.6798 divided by 0.6798, and then this divided by 0.6798. So let's divide the 3 by the smallest. And so that means potassium is going to be 1.000 to 4 sig figs. Chromium will be 0.687, 0.687, oops, no, 0.68173. Point 68173 divided by 0.6798. And chromium comes out to 1.002, and then I'm going to carry one extra digit, 8. And then oxygen is going to be 2.373. 1 divided by 0.6798. And so oxygen comes out to 3.490 sub 9. 3.490 sub 9. Are these simple whole number ratios? No. And so what we do is sometimes we'll just round it. So potassium we could easily round to 1. However, when I look at chromium, can I round that to 1? 1.002, would you feel comfortable rounding it to 1? Yeah. How about oxygen? Would you be comfortable, we got to round this down, 3.4, so that rounds down to 3. Would you be comfortable rounding that down to 3? No, I wouldn't either. And so are we out of steps? Are we out of tricks that we can use to?
But it's multiplied by the 2.
Yeah. If we multiply everything by 2, will that work? Yeah, so potassium is going to be 2. Chromium is going to be 2.0056. Oxygen will be, what, 3.4909 times 2. Oxygen is going to be 6.9818. Okay, now how about this? Okay, potassium is fine at 2. What about chromium? Should I round that to 2? Would you be comfortable rounding this to 2?
Yes.
Actually, yeah, this is pretty close to 2. How about oxygen? Would you be comfortable rounding that to 7? Is that close enough to 7? Yeah, that's probably close enough to 7. Okay, now, do you know what this substance is?
Potassium dichromate.
Potassium dichromate. Good. Potassium dichromate. Hopefully this is not one of those that they found in Palestine. So what is the name of the compound? Potassium dichromate. What is the oxidation state of chromium in this compound? Do you guys remember oxidation state? Okay, Chem 1A will have slightly different rules than Chem 4 did. Right now, here it is. So oxidation state, I had that up. I don't know why it's closed. Let's see what page oxidation state is on. 85. Rules for assigning oxidation states. Do you guys recall what oxidation states are? Maybe we should back up a little bit. Three 3-4, oxidation states, a useful tool in describing chemical compounds. Most basic concepts in chemistry deal with measurable properties or phenomena. In a few instances, though, the concept has been devised more for convenience than because of any fundamental significance. This is the case with oxidation states, or oxidation numbers, which is related to the number of electrons that an atom loses or gains or otherwise appears to use in joining with other atoms and compounds. And so the way I summarize this is an oxidation state is the apparent charge on an atom. Apparent charge. And it's apparent charge, so what we do is we compare it with other apparent charges. But it's not literally the charge on a lot of these. But it's still extremely useful because we can understand things in terms of behavior based on the oxidation states of things. So let's look at rule 1. And there are different rules depending on which book you have. But rule 1, the oxidation state of an individual atom in a free element is 0. So oxidation states of elements are 0 in elemental substances. 2, the sum of the oxidation states for all atoms is equal to the net charge. If the net charge is 0, the sum is equal to 0. If the net charge is non-zero, then the sum is equal to whatever the non-zero is. The charge is. 3, in their compounds, group 1 metals have an oxidation state of +1. Group 1 are known as the alkali metals: lithium, sodium, potassium, rubidium, cesium. Those are all +1 in compounds. Group 2 are the alkaline earths: magnesium, calcium, strontium, barium. Those are all +2. 4, in its compound, the oxidation state of fluorine is -1. Fluorine's special. Fluorine gets its preferred charge, -1. And then the others follow suit. Oh, actually, no. In its compounds, hydrogen usually has an oxidation state of +1. And so hydrogen is also group 1. But the metals get assigned first and then hydrogen. 6, in its compounds, oxygen usually has an oxidation state of -2. 7, in binary 2-element compounds with metals, group 17 are -1, 16 to -2, 15 -3. So what I do here is this. I don't really memorize those in that way. I just kind of summarize it in this way. You know, group 1, we go first. +1, group 2, +2. Fluorine. What charge is fluorine like? -1. Hydrogen? +1, and then everybody else. Who's next in line after fluorine? Fluorine goes first because fluorine is the most electronegative element of the periodic table. What's the next most? Oxygen. And so oxygen would go next, and it would be charge? -2, and then next? -3. And so that's it. Those are the rules in a nutshell. There. All right, so the homework problem is asking, what is the oxidation state of chromium in potassium dichromate? And so let's try to figure that out using the rules that we just looked at here. So which one gets assigned first? Potassium, chromium, or oxygen? Potassium charge? +1. Who goes next? Chromium? No, not chromium.
Oxygen.
Oxygen. And the charge?
2 minus.
Okay, now chromium is a transition element. A lot of these transition elements, do you know the common charges of chromium? You know, this part of the periodic table has the common charge of
1
plus
Plus
2
2, plus 3.
plus 2 plus 3. Do you guys know that? Most of the cations in this region are plus 2 plus 3. Maybe I should do the periodic table here. So it might be easier to see. Unless I closed it. Did I close the periodic table? No, I didn't. There it is. Plus 2 plus 3. I have it in my periodic table. Plus 2 plus 3. And then these guys are typically plus 1 plus 2. And then these guys here are typically 2 and 4. Right? Are you guys familiar with that?
Yeah.
This is the pattern in the periodic table. I like this periodic table. I like this periodic table with the Roman numerals. Do you know why I like the Roman numerals? Because the Roman numerals tell me the max oxidation state. In other words, the maximum positive charge in this case. And so if I look at chromium, what Roman numeral is it? 6. And so even though the common charges of chromium cations is plus 2 and plus 3, it could go all the way to plus 6. That would be the max. So in this case, I don't know. Is that plus 2 chromium or plus 3 chromium? A lot of these, when you think about plus 6, have you ever seen a plus 6 cation? No. And so this is why they said at the beginning of this section that, you know, this is just a tool that we use. You aren't going to see chromium plus 6 because that's too many electrons to lose, but effectively it's like that. You know, it's not going to be happy in this type of bonding situation. And therefore, these are variable charge. It turns out that chromium can be anywhere from 0 in the metal to plus 1, plus 2, plus 3, plus 4, plus 5, plus 6. Plus 2 and 3 are the most common, but it could be any of those other ones. So in this particular compound, what is it? And so we're going to use the other rule. The sum of the oxidation states has to equal the net charge. The net charge is 0. It's neutral. And so how many potassiums do we have? We have 2 potassiums. Each potassium is positive. How many oxygens do we have? We have 7 oxygens. Each oxygen is minus 2, or 2 minus, let's say. We have 2 chromiums. And I don't know what the charge on the chromium is. So what we're going to do is we're going to use that rule here. Okay, minus 2 times 7 is going to give us minus 14. And then plus 1 times 2 gives us plus 2. So plus 2 plus chromium. Chromium I don't know, so I'm just going to call it x. And so plus 2 plus 2x minus 14 is equal to 0. What is x?
6.
X is 6. And so this is chromium plus 6. Now, a plus 6 cation is ridiculously high as far as charge goes. That's a crazy amount of charge, plus 6. You know, it's a crazy amount of electrons to lose. And so sometimes what people do is they just call it chromium Roman numeral 6 to indicate that's not the, you know, the actual. You aren't going to find a chromium atom floating in water with a plus 6 charge. It's too unstable. It's going to be too reactive. Whereas in this, you know, in dichromate, you would find chromium 6, like that. Chromium Roman numeral 6, chromium 6. You know where they found? Have you ever heard of Erin Brockovich?
Mm-hmm.
Do you know what she's famous for?
Busting the, what was it? It wasn't a refinery, but
Yeah, there's some. It happened in the San Joaquin Valley near Bakersfield.
yeah, like everyone got poisoned from.
Right. There's like some kind of cancer clusters, as I recall. A bunch of cancer clusters there.
Deposits
from drinking the water. The water was contaminated with chromium 6. So she's very famous for chromium 6. Chromium 6, well, the water was contaminated with dichromate. Dichromate's chromium 6. Not chromium plus 6 cations, but dichromate, which contains chromium 6. Does that make sense? Well, in Palestine, they don't have to worry about chromium 6. They got to worry about other carcinogens. So let's see if they get cancer clusters there as well. But it's not just in Palestine, because the chemicals leaked into the Ohio River. And the Ohio River, everything downstream of Palestine is going to be contaminated now. And so I think nobody's going to drink the tap water there for a while, you know. But if you were to drink the tap water, you want to know how much, you know, vinyl chloride, how much of this, how much of that's in there. Because there's another Aaron Brockovich style environmental lawsuit that happened in Camp Lejeune. Have you heard of that one too? That was vinyl chloride, the same stuff that spilled in Palestine. And there was a cancer cluster there at the military base. And there's a huge settlement for that. You know, a huge settlement is not $1,000 per as an inconvenience fee. These people were sick, you know, that suffered there. But do you guys remember the names like dichromate? Remember those? And so chapter 3 also deals with nomenclature. And so I want to talk about...
Can we find the oxidation state for an ion? For instance, like a nitrate ion or something?
Okay, we'll do that too. But first, let's remind ourselves what a nitrate ion is. And so what I do is memorize these. Like dichromate. How did I memorize dichromate? I memorized it first with flashcards, but I had a hard time with flashcards. I had a hard time with flashcards because I didn't have it in my motor memory. And so when it came time for the test, I couldn't remember quite what it was. And so I gave up on memorizing it using flashcards, but you know, still people do it. That's fine. You know how I memorized it? I just wrote it over and over again. You know, by like the 500th time you've written this, it's in your motor memory. So if somebody says dichromate, you don't have to think about it. It's like walking or riding a bicycle. You know, there's very little thought that goes into it. You just write it. You know, dichromate. Chromate. What's chromate?
CrO4 2 minus.
Yeah. CrO4 2 minus. So this is dichromate. Memorize this. And then we have chromate. CrO4 2 minus. Why is dichromate, why isn't that Cr2O8 4 minus? Take two chromates, put them together. Di usually refers to 2, right? Are we out of time? Oh my gosh, I'm too far behind. I didn't stop here. Let me just quickly end with this. What are the other ones you should memorize? Dichromate, chromate,
Permanganate?
permanganate. Give me the formula.
MnO4
MnO4, not 2 minus, negative. Permanganate. Give me another one.
acetate.
Acetate. That one took me a long time. C2H3O2 minus, or CH3COO minus. Acetate. How about oxalate? C2O4
2 minus.
2 minus. Oxalic acid is.
Oh, yeah.
This is oxalate. What other ones do we have to memorize? Acetate, oxalate, dichromate, chromate, permanganate.
Carbonate?
Carbonate, we don't even use patterns to memorize that. The patterns that we use to memorize, so you got to memorize borate and silicate. What's borate?
BO3 3 minus.
Yeah, borate is BO3 3 minus. And what is silicate?
SI4 4 minus.
O4.
SiO4.
O4, excuse me.
SiO4.
Minus.
Charge?
Is it 4 minus?
4 minus.
Yeah.
So you need to memorize these. All right. So you'll want to start. The sooner you start, if you look at this every day, it's easier to memorize. So, all right. I guess we're out of time, so I'll stop here.
If you can put them into a song too.
Yeah.
Sometime memorize